Good afternoon, this is Mr. Schweitzer, and this is a little video on what is KSP. We already know, review from previous videos, that equilibrium is a competition between a forward process and maybe even a reverse process. So two processes going back and forth from X, let's say, to Y, and they're just sort of bouncing back and forth, and they reach a static balance. Now, you might say whenever something is at equilibrium that it looks like nothing is changing. But there is. It's just in balance. So quite often questions will ask, which of the following would be an example of equilibrium? It'd be one where we have something that looks like nothing's happening, but it's just in balance between multiple processes. If you see something changing, or if they tell you something is changing, then that is not an example of equilibrium. Equilibrium is where everything is essentially in balance, therefore nothing is changing. The type of equilibrium that this particular process looks at is solubility. The picture of this is pretty straightforward. You take a beaker, and inside this we simply drop in some salt or some ionic compound. Now, just so you're aware, the solubility of these things, this process generally works best for things that are only slightly soluble. Okay. So, for example, we have Ag2SO4. These are things that just aren't very soluble. You'll find a list of these things on equilibrium sheets we hand out for KSP values. And this would be an example of one. This is heavy metals, highly insoluble sulfates, things that are only slightly soluble. The math doesn't seem to work, or this model does not tend to work with things that are very, very, very soluble. All right, so again, what happens is we take some silver sulfate and we start dropping them into solution. Then, as it dissolves, of course, you know that for this compound, we're going to get 2 Ag pluses, 1 sulfate. Okay, and that's the proportions which they will be achieved in solution. And eventually, you'll start having stuff piling up on the bottom. This is by definition a saturated solution. This means that when we are saturated, and only when we're saturated, it would appear that nothing is happening. In order for this to be an actual equilibrium system, we need to have a solid on the bottom. Therefore, stuff is constantly dissolving and stuff is constantly retreating. So we have the equation as follows. Ag2SO4 yields Ag plus SO4 minus 2. Of course, we have the reverse reaction. Sometimes you'll see it with the arrow going back and forth. I don't believe that this double arrow would be a requirement at any point in time, but usually it's just there to help signify an equilibrium system. We balance this by putting a 2 here. Okay. So at some point, the rate at which these two ions can convert back to solid equals the rate at which the solid dissolves into the aqueous solution. We call this concentration here, the saturated solution, we call this concentration the molar solubility. That's the most common name for it. Molar meaning it's molarity, and this means it's the maximum you can get. Alright, and then what we want to do next on this thing is to be able to write an equilibrium expression. Now this is the dissolving equation. This is just how everyone writes it. Solid on the left side and the dissolved components on the right. And it's just describing this dissolving process. We call this thing KSP. Now the SP stands for solubility product. Now, in this case, remember we're tracking concentrations. K is a representation of the concentrations of the products over the concentration of the reactants. Any solid or pure liquid does not have a concentration and therefore cannot be tracked. This little SP here really means nothing. It means nothing for the mathematics of this particular problem. It's just a hint to you that this is the type of process we're looking at. You'll see various letters below here just signifying the types of things that they'd be working with. For example, you can have a Ka. A just means acid. Or you could have a Kb, which just means base. So again, don't get too tied up in those letters. A general one would be a Kc, meaning just simply concentration, or Keq, which means equilibrium. Again, they mean the same thing. We'll get to some of these other names later. But to write your mass action expression or your equilibrium expression, you do your concentration of your products over the concentration of reactants. Now, my products are 2 Ags, so I'm going to go Ag, don't forget your positive sign, bracket, and they have to be brackets, not parentheses, and 2 goes here representing that coefficient. Then multiply it times SO4 minus 2, bracket. Now, this means, there's a coefficient of 1 here, so this 1 goes right there. Again, we never show this 1. If you don't see it there, you'll assume it's there. And the fact that this is a solid, the only reactant we have is going to be a solid, so it's gone. You either can leave it off or you can put a 1 below. So another more common way of writing this is just going to be the KSP equals the concentration of Ag2 plus, bracket, concentration of SO4 minus 2, bracket, and this is it. Pretty standard thing that we'd want to be able to do with a KSP. One, understand the concept about what it looks like, and then 2, be able to write a KSP expression for these things. Notice that for all of these KSPs, there will never be a denominator below here. It'll always just be 1. So they're simpler versions of a mass action expression or equilibrium expression, and it gets us off on the right foot doing something just kind of simple. And that's your basic introduction to KSP.